we have this function y equals x to the power of sine x. And we're asked to find the equation of the tangent to the equation at the point where x is equal to pi over 2. Now, you've got to remember that this is not an x to the power of a number question, so you can't like bring the sine x down and then do sine x minus 1. That might be a temptation. No, that only works when you have x to the power n, where n is a constant. So we need a different strategy. And the way you deal with this is essentially we know how to differentiate exponentials like e to the x. I mean, this is a sort of this is an exponential. We know how to differentiate e to the power of a function even. So let me just write down that d by dx of e to the f of x, well, that equals e to the f of x, because that's how you deal with an exponential. Sorry, particularly e, and then using the chain rule, we will times by f dash x. Basically, you differentiate e to the f of x with respect to f of x, and then you times by the derivative. I'm not going to go through all the like letting u equal f of x and using the chain rule. You should be familiar with that. But that is an important result, and actually it's going to be crucial for what we do now, because I'm going to try and write x to the sine x as e to the something. And to be able to do this, this is what I have to do. I have to write it as e to the ln x to the sine x, because these two cancel each other out. They're inverse operations. And I've done that. This is your standard way of dealing with that sort of thing. Like if you wanted to differentiate 2 to the x, okay, and you couldn't quite remember the rules and stuff, you would deal with it. That's exactly what you would do. You would write it as e to the ln 2 to the x first. And then the next step is to use the third rule of logs and bring it down. So it's e to the sine x ln x. And suddenly, and this one here would be e to the x ln 2, which is very similar to e to the kx. It's just that k is equal to ln 2. That's how you deal with those. It's a bit more complicated here, but like I said, we can use the chain rule. So dy by dx is going to equal e to the sine x ln x. Going to stay as it was. And then we're going to times by sine x ln x differentiated. And for this, we just use the product rule. So it's going to be, if I differentiate ln x, I get 1 over x, so 1 over x sine x. And if I differentiate sine x, I get cos x, so it's going to be cos x ln x. And remember, e to the sine x ln x was none other than x to the sine x. So I'm going to write it back like that at the end. And that is our answer for the derivative. Now, there is one other way of getting this derivative, and I want to talk about it because it is a really neat way. It's just like if you've never seen it before, you might not think to do it. It's like a topic that's, you know, I think it's taught in further maths, and you might see it, but it's like it's unlikely to be something that you think to do yourself without having seen it first. To differentiate this, we can actually do it by something called logarithmic differentiation. And essentially, we take logs of both sides first. But like I did before, I can bring this down to sine x ln x. And now, we've got something similar to before, but I haven't dealt with all this e to the stuff. Now we differentiate. And what we do is we will differentiate this ln y with respect to x. So using the chain rule, that will become 1 over y, because we differentiate with respect to y, and then we times by dy by dx. It's like when you deal with your implicit differentiation, like y squared. If you differentiate y squared with respect to x, you get 2y. You just differentiate it like normally, and then you times by dy by dx. It's exactly the same. And then we use the product rule, just like before. plus cos x ln x. And then if I was to times through by y, well, remember y is this x to the sine x. I get the same thing as before. So it's pretty neat. Like whenever you have something like this, it's actually an alternative route, potentially simpler route to what I had to do over here. Now, we're asked for the equation of the tangent, remember, when x is equal to pi over 2. So when x is equal to pi over 2, well, I need my value for y, first of all. So that is going to be pi over 2 to the power of sine pi over 2. But sine pi over 2 is just 1. So I just get pi over 2. So I've got my coordinate, and then dy by dx is going to equal x to the power of sine x. Well, that we just literally figured that out. That's going to be pi over 2. And then using the product rule, it's going to be sine pi over 2, which is 1, divided by pi over 2. Well, 1 over pi over 2, you just flip round to 2 over pi. And then I'm going to add cos of pi over 2 times ln pi over 2. Well, cos pi over 2 is 0. So actually, I just get this, and I'm going to get an answer of 1. Using y minus y1 equals m x minus x1. You might even be able to see the equation straight away, but it's gonna I'm just gonna do it like as you normally would do it. Actually, in this case, these are going to cancel, like the 1 disappears, and the answer is simply y equals x. That was part A. Part B asks us to prove that this tangent, y equals x, touches C at infinitely many points, i.e. that it is a tangent at infinitely many points. So not just that it is like a tangent here and then it intersects. No, it's got to actually sort of be a tangent here as well. And not just there, like infinitely many points. Now I made that mistake when I did this question. I just found out where it intersected, showed that it intersected at infinitely many points, but not that it touches. So we've got to make sure we do that as well. But the intersecting part is going to be the first step. So when they intersect, x will equal x to the sine x. We can take logs, just like before, and bring that sine x down. This gives two possibilities. Either ln x is equal to 0, or sine x is equal to 1, which means that x must equal 1, or we now need to think about where sine is equal to 1, and it's going to be pi over 2, or if we add on 2 pi, pi over 2 plus 2 pi, or we can add on 2 pi again, pi over 2 plus 4 pi, and actually the proper way of writing it is to say it's pi over 2 plus 2n pi. It's always a multiple of 2, where n is going to be, um, well, actually, we're just looking at positive x. I've forgotten. Yes. So it's going to be that n is technically a natural number. That's your numbers 1, 2, 3, but it's a natural number that can also include 0 because that was our first one. I don't think it's absolutely essential to write that. If you just maybe say n is a a positive integer or 0. Now it could also be tempting when I did this, when I looked at this first of all, it could be tempting to say, oh, this is x to the 1, so it must be that sine x is equal to 1. But then you miss the solution of x equaling 1, because 1 to the power of anything is equal to 1. So just be careful. It's not okay to stop here, however. We have shown there's infinitely many points of intersection, but we haven't shown that it's just touching. So what I'm going to focus on is not this x equals 1. Not really bothered about that. It's going to be this here where where it's just touching. So when x is equal to pi over 2 plus 2n pi, y is also equal to pi over 2 plus 2n pi. Remember, because y is equal to x. I know it's where they intersect, but it's where this intersects y equals x to the sine x. And furthermore, dy by dx will equal, remember this is the gradient of x to the power of sine x. And if I go back up here, basically we want to show that the gradients are also the same. Then it must be a tangent. So it's going to equal pi over 2 plus 2n pi to the power of 1, so I can just ignore that. And then I'm going to sine x again is going to be 1. And then I'm going to divide by x. And then crucially, this term is 0. So I will get 1. And therefore, the curves intersect and have the same gradient. In infinitely many places. As n varies. So y equals x touches y equals x to the sine x. You know, maybe I've gone overkill here, but I think showing that they intersect in infinitely many places, not too bad. And when I first did this question, I literally said sine x equals 1 has an infinite number of solutions, we're done. The subtle part is actually no, we have to show that it touches in infinitely many places. So we need to do more than that. We need to find all these points of intersection. We can ignore that one, although you can write that one down. And then we've got y equaling the same, and also that the gradient function is equal to 1. That means that y equals x and y equals x to the sine x have the same gradient at each of these points, which implies that it's a tangent there. Okay, subtle. Just going to show you to finish the graph of these functions. So this is actually courtesy of Desmos. We've got y equals x in blue, and then y equals x to the sine x in red. And we can see about pi over 2 at 1.5, there's a tangent. And then really interestingly, that this is what it looks like. Okay, you can see that it's always a tangent. It just carries on like that. What a cool curve. Now, I just want to talk finally about x equals 1. Really interesting. It's not quite a tangent there. It actually intersects there. So you wouldn't get the same gradient function when x is equal to 1. You'd get a different dy by dx if you put 1 into the derivative. So I ignored that one, but you can sort of see if it's going to be an infinite number of places, like that one wasn't ever going to be even if it did, even if it was a tangent there, doesn't matter. I've shown that the other ones are have the same gradient at those points. Okay, thanks.